Okay, hi everyone. Chapter 11, sections 1 through 3, probability. Probability is something different than we've encountered so far in mathematics. Most all of mathematics, except for probability and statistics, has a definite answer. You ask what's 2 plus 7, and there's no probability about it. The answer is 9. Either you're correct or you're not. With probability, the whole point is that we don't know what the correct answer is, or not what the correct answer is, but what the outcome might end up being. Could be several, one of several things. And so what we can do is to calculate correctly what the probability of those outcomes is, but the point is it's just probable. We don't know for sure that it's going to happen, not unless the probability is equal to 1. So we can illustrate a lot of the ideas of probability with just tossing a die. So suppose we have a fair six-sided die. You know, get it from a casino or something like that, and it has sides 1 through 6. And so let's answer the following questions. First of all, what are the possible outcomes? That's the first question, and there they are, 1 through 6. So I'll say question number 1 is, what's the probability that you got a 2, for example? Well, if they're all the same, if it's fair, which means they're all equal probability, and if you have 6 sides, then each of those is going to have 1/6 of a chance. And so that's the answer to that one, and that, of course, is generally true. If you flip in a fair coin and you have a fair coin with 2 sides, then the probability of each one is going to be 1/2, and so on. Okay, and what's key here is that the probability of any event, no matter what that event is, will always be something between 0 and 1. To say that it's 0 is to say that it will for sure never occur. To say that it is 1 is to say that it will always occur. Okay, so that's important. Here's another question. What are the odds of landing on 2? Okay? What are the odds of getting a 2 when you throw a die? The word odds is slightly different from probability. Probability, it's 1 out of 6. Odds, you say, well, the chances of getting it are 1. The chances of not getting it would be 1, 2, 3, 4, 5. And so the way you write that is to say 1 to 5. Okay, so you can see the relationship here. Probability is 1 out of 6. The odds are 1 towards it, 5 against it. So that's just another word that's used. This isn't used much in formal probability theory, but you find it in racetracks and things like that. So anyway, that's good. What's the probability? What's the probability of, I'll just say, of 2 or a 3? What's the probability of landing on a 2 or a 3? Well, these are disjoint events. They can't both happen at the same time. So the answer to that is you just take the probability of landing on a 2 and you add the probability of landing on a 3, and each of those are going to be a 6. The 6 plus the 6th is going to be, I'll just write it like that, a 6 plus the 6th is, I'll just leave it as 2/6. We could simplify it to 1/3, but let's just leave it as 2/6. Okay, so that's the probability of a 2 or a 3. What's the probability of not landing? Not landing on 2. What's the probability of not landing on 2? Well, if you don't land on 2, that means you've landed on either a 1, 3, 4, 5, or 6. So if I wanted to, I could say, well, the answer is it's the probability of landing on a 1 plus all the way up to 6, leaving off the 2, of course. And by the time you're done, you're going to get 1, 2, 3, 4, 5. So you're going to get 5 out of 6. But another way of thinking about this is that we know that one of those things has to happen. We know that one of them has to happen. So another way of thinking about it is either you've landed on a 2 or you didn't. the probability of landing on a 2 is 1/6, so the probability of not landing on 2, here's the way we write it. It's the probability of not. You put a little tick there to indicate not. The probability of not landing on a 2 is equal to 1 minus the probability of landing on a 2, and that's of course equal to 1 minus 1/6, which is 5/6. Okay? So that's the probability of not landing on a 2. Okay, very good. Here's the next one. E is the event of land on even number. So you want the probability of E. Well, how many even numbers are there? There's 2, 4, and 6. So if you add 1/6 plus 1/6 plus 1/6, you get 3/6 as your answer. Do you agree? Let's let number 7 be T, which is the event of landing on multiple of 3. The event of landing on a multiple of 3. Well, there's 2 multiples of 3 in here. 3 times 1 is 3. 3 times 2 is 6. So if you add those together, the probability of that happening is going to be 2 out of 6. Do you agree? Okay. Number 8. What's the probability of E and T? Another way of writing that is probability of E intersect T. Do you remember what intersect means? It means that both of those things are happening. Something is in the intersection of 2 sets if it's in this one and also in this one. So you can write it either way. And so what's the probability of being in both of them? Well, let's see. Let's figure it out. These were your even numbers right there. And these are your multiples of 3 right there. And so there's exactly one of them, which is both an even number and a multiple of 3. So that's the probability of getting the 6, and that's equal to 1/6. Okay? Number 9. What's the probability of E or T? Which you can also write like this. Remember what the union of 2 sets is? The union of something is in the union means to be in the intersection means it's in this one and in this one. That's the intersection. To be in the union means it's in this one, or possibly both of them. But the point is it's in at least one or the other, okay? So it's in one or the other. That's the union. So one or the other. And so what are the choices there? All it has to be in is one or the other. So you have 1, 2, 3, 4. So the answer is 4 out of 6. And remember what we learned with sets? The number of things in the union of 2 sets, let's just say A union B, is the number of things in A plus the number of things in B. But then what did we have to do? We counted these twice, and so we have to get rid of them once. And so we subtract the number of things in the intersection. Remember that? That's a formula for this. And here we're going to have the same sort of thing. The probability of being in both of them is basically you take the probability of being in E and you add to that the probability of being in T, but then you have to compensate for the fact that we counted this thing twice, and so we have to subtract the probability of being in both of them, which is E intersect T. Okay? So there's the idea. Very good. Okay. Now, one more thing, and then I'm going to have to start erasing. I'll do it up here. Definition. A and B are mutually exclusive. Mutually exclusive if the probability of A intersect B is equal to 0. Means that there's no chance that something can be in both of them. Okay, that both of them occur at the same time. Okay, there's no chance at all that both of them occur at the same time. If one of them occurs, you know the other one did not occur. Okay, so for example, the probability, or let's just say it like this, 2, the event 2 and the event 5 are mutually exclusive, right? Because if this is what you rolled, then you did not roll this. So the probability of getting a 2 and getting a 5 is 0. You can't get both of those at the same time. Either if you're assuming you just rolled once, you got one or the other. Okay, so that one is mutually exclusive. So here's the question 10. Are E and T mutually exclusive? And I guess we already know the answer, don't we? Because the probability of their intersection is equal to 1/6. So the answer is no. And why is that? Because they both can happen at the same time. There it is. They both happen. They both could happen right there. If you get a 6, they both have happened. Which is not equal to 0. Okay? So that's what it means to be mutually exclusive, is if they both can't happen at the same time. Okay, very good. So now let's erase all of this and ask, we'll keep this right there, but ask another question. If you go to a casino and ask for a die, you will get a die that has the various sides, and let's take the side with 5 little pips on it. I think those are called pips. And you'll notice that the die might be white and these pips might be red, and they've got a little indentation. So they've got a little indentation there where they've colored this red. But then this little place where you have that little indentation, they fill that up with more plastic, with the same plastic as the die, I imagine, so that the whole thing, no matter how many pips you take out, each side weighs exactly the same. Because if the sides didn't weigh exactly the same, if the side with 6 of them, say, is going to be lighter than the side opposite it with just 1, then it would be just a little more likely that this one would end up down and this one would end up showing up, right? Because the heavy side would slightly more likely go down. And a casino can't afford that, okay? They have to have everything be ideal probabilities, because that's how they make money, is by, if they know what all the probabilities are and that they're all equal here, then they can calculate how much money they're going to make statistically, okay? They can be not sure, but at least very confident. But they want to make sure that there's nothing wrong with the die. But say, go back to our example, say we've got just some cheap ones that we've got at home that don't have those pips filled in, okay? So one side might be a little lighter than the other. So then we can't assume that each one of these things, we can't assume anymore that the probability of whichever one you want to take, let's just take 5 here, is equal to 1/6, okay? Question is, how can we determine what the proper probabilities are? If you have a die which is, not filled in, or maybe it's misshapen or something like that, how would you go about figuring out what the probabilities are if you can't just mathematically be sure that it's right to call them all 1/6? And if you think about that, you think, well, let's do this. Let's just take this die, and we don't know how what's gonna happen, and let's toss it 30 times. We'll toss it 30 times, and then whatever the ratio is, if we end up getting You know, if we get maybe, okay, we toss it 30 times, and so here's your 1, 2, 3, 4, 5, and 6, and maybe you got 5 here, maybe you got 7 here, maybe you got 7 here, maybe you got 5 here, maybe you got 6 here and 6 there, just as an example, okay? So maybe that's what happened. Question is, should you take those as the probabilities then? That it's going to be 7 out of 30 and 7 out of 30 and 6 out of 30 and 6 out of, or no wait, this is out of, wait, this all has to add up to 30. 1, 2, 3, 4, 5, 6. I had it adding up. Oh, let's say we toss it 36 times, okay? We toss it 36 times. I think those all add up to 36. Then you get these for answers, okay? Then the question is, should those be the probabilities that you assign? Should you assign 7 out of 36 for this one and 5 out of 36 for this one? And you might think, well, you know, who knows? It would be more justifiable if instead of doing it 36 times, we did it 360 times. Agreed? If you did it a whole lot more times, then you're going to get different numbers, but those are more likely to give you the true values. And if you wanted to be even more sure, you'd say, well, let's not do it. Let's not stop there. There's no reason we have to take multiples of 36, but we'll take it 3,600 times, okay? The point is, the more times we do it, the more likely, assuming we're rolling these fairly each time, by the time you just keep doing it over and over again, these, whatever proportions you get, those are going to head towards the true value, whatever that true value is. And this is called, there's actually a mathematical term here. It's called the law of large numbers, which basically just means that it's what your intuition tells you. That if you have a coin and you want to see how often it's going to go heads, you don't do it once. If you do it once, you're going to get maybe 1 head. Does that mean it's going to give you a head every time? No, of course not. If you do it 10 times, you might get 7 heads and 3 tails. Does that mean it's going to do it 70%? No. By the time you get to 100, it might be at 55 and 45. By the time you get to 1,000, it might be 490 and it might be 510. So the point is, as you go farther and farther out, you're going to get closer and closer to whatever the true probability is. Okay, whatever the true probability is. So anyway, so we either assign probabilities by assuming what they are by thinking of the mathematics, or else by discovering them by just performing the experiment over and over and over again. Okay, so that's kind of an important distinction to make, that you do one or the other. Okay, very good. Last thing, I'm going to give 3 different lessons on probability, and in each one I want to do kind of an interesting problem, and at least one interesting problem. And here's the first one. It's called, because this just shows that that our common sense is sometimes goofed up. So this is going to be, I tell you what, I'm going to do this one. No, I'll do the birthday problem. I'll call the birthday problem. Okay? And here's the question. There's 2 parts to it. First of all, we're going to assume that 365 days in a year. Okay, I realize that every 4 years you have a leap year, but let's just assume it's 365. Most of the time, that's what you have. Okay? So given that, assuming, so February, if anyone's born on February 29, we'll assume that we'll lump them in with February 28 and call that all one day. Okay? So here's the question. How many people do you need to have in a room before you can be absolutely certain, that is, the probability is equal to 1, absolutely certain that there will be at least 2 people with the same birthday? Okay? don't worry about the year, just the same birthday. Okay? How many people need to be in the room before you can be absolutely certain that there are going to be 2 people with the same birthday? Well, let's think about it. Here, there's 365 days of the year. Let's list them all out like this. There they all are, just like our counting problem. Okay? If you had 15 people in the room, one could have a birthday that day, and one could have one that day, and one could be there, right? If you have 50 people in a room, they could, be all over these places. Agreed? If you have 365 people in a room, then it's possible, not very likely, but it's possible that each of those people have a different birthday, because you have 365 slots and you have one person for each slot, and so they could all still have distinct birthdays. Agreed? 365. But as soon as you get to 366, then you've already filled up all the slots with one person, and now with that 366th person, you've got to put them someplace, and as soon as you put them someplace, you've got some date with 2 people there. That is, you've got 2 people with the same birthday. Agreed? So the answer is to be, so probability equal 1 of, I'll just say same birthday. The answer is 366 people. Okay? So that's a pigeonhole problem. Okay? I guess it's probability, but it's really more of a counting problem. Okay, here's the second question. How many people do you have to have in a room before the probability is greater than 1/2 that 2 people will have the same birthday? Okay, so now we're no longer guaranteeing anything. We're just saying that if you had to put money down on it one way or the other, that you'd be better off to put money down assuming or claiming, guessing that there's going to be 2 people in that room with the same birthday. Okay, how many people? Well, when I ask this question to classes, this is where it's tough having a video, but when I ask this to to my classes, the answer that comes off as much as anything is something like 182 or 183, basically half of this number. Okay, and that's one guess. Other people guess different things. It's a rather amazing answer, though. Here's the way we do it. Let's see if we can figure it out. Okay? Suppose there's just 5 people in a room. Let's just take this as an example. What are the chances that those 5 people have different birthdays? Okay, they have distinct birthdays. No same birthday. They're all different. What are the odds? Well, let's think about it. What you have to count all the possibilities. First of all, if you have 5 people in the room, what are all the possibilities for their birthdays? The first person has 365 choices. The second person has 365 choices. This is just saying in general. If you have 5 people in the room, this is how many different choices you have for birthdays. Okay, they each have that many. That goes back to our counting problem of the last chapter. And now, how many of those are going to have different birthdays? To have different birthdays, the first person would have this many choices. The second person would have this many choices. The third would have this many. The fourth would have this many choices. And the fifth one would then have this many choices. Agreed? So this number divided by this number is the probability that they all have different birthdays. Agreed? This is the probability that they have different birthdays. And since that's the probability that they have different birthdays, 1 minus that is then, what's the opposite of them all having different birthdays? What's the complement of that? Either they all have different birthdays, or at least at least 2 have the same birthday. That's the complement. Agreed? Either they all have different or they don't all different. If they don't all have different birthdays, then that means at least 2 of them have the same birthday. So this right here is the probability they all have different. 1 minus that is the probability that at least 2 have the same birthday. Okay? So we can do that for any number of people. With 5 people, this is your calculation. If you want to go to 10 people, then you do the same thing. You do this out to 10 and you do that out to 10 and you calculate that. Okay? So the calculation is pretty simple. It turns out that by the time you get to 23, and you take this list out 23 and you also take this out 23 and then you subtract it from 1, it turns out that this number here is less than 1/2. It turns out that if you have 23 or more people in a room, the chances are, that is, the probability is greater than 1/2 that at least 2 people will have the same birthday. Really surprising, okay? Really surprising. It's kind of just shows you some of the surprising things that comes with probability, okay? So if you're ever in a room with 30 or 40 people, you're almost guaranteed that there's going to be 2 people with the same birthday. All you have to do is just go around the room and have everyone yell out their birthday, and if anyone hears their own birthday, then to speak up, and you'll find that there's a match. Okay, if you have less than 23 people, sometimes I have classes with 15, and if I do that, then I tell everyone to take their own birthday and to take some friend's birthday. So everyone has 2 birthdays, and you do it that way. So it's not a guarantee. There's no guarantee until you get to 366, but once you get past 40 or 50, this number gets to be very big. The chances are very good that there's going to be 2 people with the same birthday. Okay, so anyway, there's your first lecture on probability, and we'll continue with this in the next one.